Thank you very much. It's a great pleasure to actually be here, and I would like to thank the organizers, and in particular Ionut and Luminita, for putting together a fantastic program and for inviting me here as well. It's been really fantastic, and I've learned a lot. And being one of the last speakers and having to take care of my dance now, so I'm smiling enough, I actually changed a little bit what I was going to say, and I hope I'll get through most of what I want to say. So a kind of alternative title is sort of some buzzwords: integrability, universality, and turbulence in some sense. And the idea is I work in cold atoms. I've never really worked in helium, but obviously there's relations. But recently I've been working on cosmological scales, so I hope I'll get to that part and how it all ties together. So what's the main framework of the presentation? Well, by now we've heard all about two fluid models in helium and so on quite a lot. And you've seen this picture a few times. This is an atomic Bose-Einstein condensate in a harmonic trap. And you see that if you go to zero temperature, you basically have something which can be deemed a pure condensate. But as temperature increases, then the other component, the non-condensed component, comes into play. And so you have a standard kind of picture that you have a condensate sitting in the middle and a thermal cloud which coexists with the condensate but extends a lot further. And so the idea is, what does that do along the lines of, for example, we heard about mutual friction in quite a few talks and so on. So what are the things I would like to talk to? And I may not get through all of them. I might skip through something to get to the end. So I want to talk firstly, this is a new thing that came in because I heard many talks talk about soliton and vortex. And then there was the question, do we include sound? And what is the role of sound? And so on. And this is kind of a rather old project, but still has interesting questions, particularly on the mathematical scale. So if you have a soliton and a vortex, what are the interactions with the sound, and in particular the context of a quadratic potential? I'll talk a bit about finite temperature. What are the models we use? This is the analog of the two-fluid model, but for a gas, and then there's a stochastic model. I briefly introduced this in the, whatever it was called, round table on last Friday. And I'll try to tell you what these mean in the context of solitons and vortices, because of the coexistence of the non-condensate. And then I hope I have quite some time to talk about universal features. So the idea, how do we get from something which is not condensed to something which is very condensed, and what universal features arise during this process. And then switching completely gear, what happens if you have cosmological condensate, and what on earth is a cosmological condensate? Why should a galaxy behave like a BEC? Okay, so starting with something quite some time back, I'm sure you recognize some familiar faces here. This project was started actually while I was still a postdoc at Durham with PhD student at the time, Nick Proukakis, and then there's been quite a lot of work ongoing intermittently, to use that word. That's the only time you'll hear about intermittency in my talk, I'm sorry to say, during that whole time. So you've seen these pictures in at least one talk. The idea is you have an atomic condensate, so let's think of it like an elongated condensate, and you have a soliton, and it's kind of oscillating inside there, a dark soliton. And you can have two solitons, and they can be bouncing around each other, and then the idea is you can model all this very nicely with the Gross-Pitevsky equation. So the context initially for this first part is just Gross-Pitevsky equation, and then we have, it's one dimension, and we have a quadratic potential. In the absence of a potential, we know this is a fully integrable system. That's why we have these dark solitons. So what is the role of this potential? So the kind of setting is this. We have a condensate trapped in a harmonic trap. So this is the density, and then you have a dark soliton in there. And what happens, we've heard a lot about that, and you can derive it. The soliton oscillates in the trap, but not with the trap frequency, which is the frequency that any emitted sound waves will move, but with a different frequency. So in perfect 1D, it would be a square root of 2 difference. And what you see is the soliton oscillations. Now, why is it oscillating? When the minimum hits zero density, it just bounces back, and it just oscillates back and forth. But you see all this background here. There's all this extra stuff that people never really talk about. So let's think about it. What is this extra stuff? Just think about sending a soliton through a fluid, a dark soliton, on a barrier. Okay? If you set it on a barrier, it doesn't have to be a steep barrier. It could be a smoother. I'm just trying to show the most extreme point here. Of course, if the barrier is very high, it will bounce off. No sound emission. Perfect elastic collision. But if it can actually emits sound as it's bouncing off. You see these sound waves propagating backwards and forwards, so positive and negative density waves. And basically, if you actually go to the case of transmitting, you see that there's a lot of sound waves. So what happens to all of that when we have a quadratic trap? Because we always have a potential. We're never moving in a smooth background. So what happens essentially is we have this sound emission, okay? And I stress very strongly, if you have a quadratic trap, this is the key to everything. Most people who solve it in a quadratic trap. This is only magic. It only works in a quadratic trap. The emitted sound is fully confined and fully coherently reabsorbed periodically. So if we measure the soliton energy by looking, for example, at the energy minus the background energy in the region around the minimum as it's moving along, I will see that, yes, sure, it has some structure, but this is a very small oscillation. Effectively, it is constant, apart from a very slight oscillation. So there's no net energy decay. So the question is, can we actually see this decay? Well, what we thought of doing in first instance is let's allow the sound to escape. So we put the trap in another trap, and we vary this height such that the sound can escape, but not the soliton. So let me play this movie, identical initial conditions, but here you will see the sound wave is allowed to propagate to infinity. We have a very large grid and it never comes back. You see the soliton dies away just because of the sound it's emitted in here. The only thing I've allowed is for it to escape outside of the trap. That's the only thing I've done. I haven't changed the trap or the initial condition. If I now look at the energy, I again have some periodic structure, of course, associated with the motion, but it's a very, very clear decay. So the soliton is losing energy. It's getting shallower, it's moving further out, and it dies away, becomes a sound wave. So this rate of emission of sound, okay, this rate of loss of energy is proportional to the acceleration squared, or if you like, if you measure a local deformation from a homogeneous one, it's proportional also to the deformation squared of the soliton. Okay, so that's what's going on. So this, you see, it's kind of deformed. If you measure it locally, you will see it's different from the one with a homogeneous background. Okay, so in this context of this setting where we allow the sound, we make it a bit more realistic. We put a double harmonic trap rather than homogeneous outside. And we look at the motion of the soliton in two different cases. If this is very high, the sound cannot escape. It's co-trapped. So harmonic, it's like you have a single harmonic trap. Then what you see is a perfect oscillation. But if you allow sound to escape, you quickly see a decay, this so-called anti-damping, because it's getting shallower and shallower and moving further out. Okay? You see there's a lot of sound waves coming from the outer trap as well, but that's, and that will ultimately mess your picture. But really, the key point is there is decay going on here. And then we thought, maybe this is not clean enough. Let's do something else. Let's put it in a Gaussian trap. We all know, okay, Gaussian trap, harmonic trap is the same if you go to the bottom. But play with how large the condensate is in relation to this Gaussian trap. So how far up the non-harmonic Gaussian nature we are probing. And so you can see this is a completely closed trap. If the cutoff is very high, so effectively I'm just probing the harmonic regime, it's perfect, no damping. It's just coherent reabsorption. But already for a V0 twice the chemical potential, actually within a single trap, I get decay. So the decay just happens by moving into something that is not completely harmonic. And we've tried other potentials and adding other barriers, and that will just kill your soliton. So it's really specific to a quadratic trap. But it's not just about dark solitons. Let's take it one step further. You put vortices. We do the same experiment. Either a single trap or a double trap where we allow the sound to escape. And let me play you this movie. So we know that as the vortex normally would like to move in a circle, but as it's moving, it's experiencing a force, and therefore it's emitting in this dipolar pattern. Oops. Not sure why the movie didn't play. So what you see, very quickly, it spirals out and dies. So this is just because you've allowed the sound to escape. And again, the rate of energy loss is proportional to the local acceleration squared. So this is a very interesting thing. I've very loosely mathematically, I'm clearly not a mathematician, termed this quasi-integrability. Particle number is conserved, okay? Energy is conserved. So it's not really an integrable system, but at the same time, with a quadratic potential, when you put these defects in, actually it is completely there is no dissipation or anything. And this is something I've been trying to motivate mathematicians for more than 20 years now to actually study. There has been some stuff, so we were motivated for this expression already. There was a paper in optics deriving these very analytically in the context of a homogeneous background. Then I think there's been some work of Panos, maybe with Pelinovsky or somebody. But I think there's still yet to be understood, a lot to be understood here. Effectively, yeah, you have the sound waves, I think, if you would run long enough. But in 1D, you basically don't get perfect thermalization in 1D. You have to run really, really long to get thermalization real time. So it's just dephased sound waves that are moving around there. And you probably wouldn't really see them. They wouldn't create such a huge effect. But you would no longer have the soliton moving in them. And just to reiterate the importance of that, actually, you can engineer, and we have a few more papers, I'm not citing them here, where you play around with adding some puddles around here, periodically oscillating, and you can change the state of the soliton from a very shallow to a very dark, just by actually, so you can make it deeper, just by actually pumping in the right amount of energy at the right time. Yes. 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 Well, you have, I mean, what you have is you have a circular trajectory. The circular trajectory is not because of the vortex moving there. It's because of the vortex emitting sound and reabsorbing. Now, yes. No, it's exactly the same. It's exactly, yeah. Yeah. Ah, okay. If I had here also an external trap like that, it would bounce back, but you would have lost your vortex. I don't think you, because it's a different trap, and therefore it would dephase the wave, so it would never sort of coherently reinteract.
Even in the harmonic trap, it's not perfectly achievable. Never the perfect circle.
Yeah. So absolutely, there is all that, but the key message is that the fact that it's so well behaved in a quadratic trap is precisely because it's a quadratic trap and nothing else. And this is, I think, rather underappreciated fact. Okay, so I'm going to try and switch gear now and move to finite temperature. And obviously, to move to finite temperature, I have to introduce a little bit what are the models that we're using. Okay, because otherwise it makes no sense. But the aim is to apply these models to solitons, vortices, vortex tangles emerging randomly, and so on. So again, here's the standard picture. If you're at a temperature below the critical temperature, you expect to have a mixture of a superfluid and a normal fluid. So typically, people use two equations, okay, fluid equations for these two components. And the easiest analogy you can think of, well, since I have a similar pattern for the fraction of atoms in the condensate as a function of temperature, if I'm somewhere in the middle, I must accommodate both for the condensate and for the non-condensate part. Okay, it's effectively the analogy of the normal and the superfluid part. And so one way to describe the system, but not the only way, is to have this kind of two-fluid picture, but now from a gas perspective, if you like. Okay, so obviously so far I've been discussing in the context of the Gross-Pitaevsky equation, and it's a fantastic model. I'm not trying to invalidate Gross-Pitaevsky, it's truly fantastic. But there are cases where you have to account for these extra terms and see what exactly they produce. So let's go back to the drawing board. Since in cold atoms we typically have sort of harmonic oscillators, this is a cartoon basically in harmonic oscillator levels. Of course, with interactions, this is a lot more complicated, but this is just a cartoon picture. So the condensate will always be the self-consistently ground state determinant of the system. And it will obey a Gross-Pitaevsky equation where it will have this nonlinearity here. This is mod phi squared. And this accounts for all the interactions within your condensate. Now, if you have a non-condensate component, so particles populated in all of these modes and they spatially coexist, then what you have is the condensate will be moving inside this thermal cloud density. It's effectively creating a new density, a new potential to trap because there's repulsive interactions, the condensed atoms. And so we have to account for that. But the interaction between condensate and non-condensate is not just a mean field interaction where one moves through the other. There is also particle exchange, okay? I do something to the system, effectively I can pump particles into the condensate or out of the condensate. And I have to allow for this mechanism. So this term here, if it's 0, there's no net particle transfer, but in general, this will allow for this particle transfer. So if I have particle transfer, then I can no longer think of this as static, basically, and I have to have an equation of motion describing this non-condensate component. Now, what's the relation between these two? There's an N here, and there's an F here, okay? N does not depend on momentum, so F also has momentum dependence, and I'm sure you all recognize this as the standard Boltzmann equation, okay? Boltzmann equation of classical gases. If you would throw this away, that's just a standard full Boltzmann equation. Okay, so what are all these terms? Well, I told you already about mean field coupling. The condensate is moving through the thermal cloud, but the thermal cloud itself will also be moving through a field that sees the condensate. Okay, so there's an effective potential here, which is not just the trap, but also this mean field term for the thermal cloud. But then if you have particle transfer, well, if they leave the condensate, they have to go somewhere, so they go to the non-condensate. So these two terms are basically the same thing, just viewed differently. There's a transfer of particles from one component to the other. Okay, and if you ask what is this other term here, C22, so here 1 stands for condensate, 2 stands for thermal. C22 means thermal collisions. This is just a standard collisional term you have in Boltzmann equation, okay, classical Boltzmann equation. So this is basically the generalization of the classical Boltzmann equation to couple to a condensate and allow for particle transfer. Okay, yes. Yes. So C12 is proportional to the condensate density times an F, 1 plus F, 1 plus F minus 1 plus F, 1 plus FF. Linear in? No, it's basically like you have 3 particles. You have basically a collision, 2 particles from here, one goes here, one goes there, basically. Okay, C22 basically has 2 particles colliding here, let's say, one goes here and one goes there. So it has F, 1 plus F. I mean, C22 equals 0 will give you the Bose-Einstein distribution, basically. Effectively, yes. That's, I mean, there's 2 components to friction. There's one moving through the other, which comes through the mean field, but then there's additional damping and complications coming from the C12 and IR. Okay, so it turns out, I will show you in a minute, you can describe a lot of things, forgetting about the collisions, particularly if you're at not too high temperatures, forgetting about the collisions, but it's important that you don't just put a static thermal cloud, but you solve dF by dt equals 0. That will add you a lot of damping just by this, allowing sort of the particles to move around between levels. So what does that do for a soliton? This movie will keep repeating itself. This is in a quasi-1D system now. So at 0 temperature, Gross-Pitaevsky, you imprint a soliton, it will oscillate backwards and forwards. You will see it start again in a minute. But if you have thermal cloud, it will actually dissipate even in a perfect quadratic trap, the point I was saying before about quasi-integrability. So let's see it. It starts identically, and you see the thermal cloud dissipates very much. If you would look at lower amplitude, you would see these sound waves. It's a matter of what you are plotting, you know. Here we're just focusing on the soliton motion, but of course there's a lot of sound emission, and you can see a little bit of that in these images here, but we could characterize more. So as temperature increases, basically you get this dissipation of the dark soliton. Okay, so it dies out, and it dies out rather quickly, and this is probably about half Tc or so it's not even very close to Tc. Here you have Tc, okay. So basically this says, okay, you should be able to get an oscillation unless you're not at very high temperature, and that was all before all these observations of the soliton oscillations, although they were anticipated, they had not been experimentally observed. So let me come to these experiments then. These are the first experiments. Okay, this is a rather poor experiment, and I haven't shown you intermediate images here. The idea is, imagine you have a solid, an elongated condensate, and you imprint a soliton, then it wants to oscillate this way. But now you're allowing the system to expand, and so effectively you should be looking at the direction of motion of the soliton being in this direction. Okay, so this is your dark soliton. They have some intermediate ones. They can actually see a coherent thing moving, but after a certain time, it's not really clear. It could still be here. It may have died away, right? It's not completely clear. So if you do Gross-Pitaevsky, you will see clearly what the pattern is. It goes to the edge. There's also some sound waves emitted from your imprinting, but then it bounces back and it does this periodic motion. But if you solve with this finite temperature model and you put the right amount of temperature for this experiment, you see the soliton goes there. It might be here, maybe not. It's impossible to tell from this image. But then it's never really visible again. It never bounces back. Okay, that's because the thermal cloud has killed basically the soliton propagation. Okay, so this is kind of on the same time scale as what was seen in the experiment. What about a vortex then? Well, we said the vortex in a quadratic potential would just be going round in a circle, okay? If it's off-centered, it will actually, at finite temperature, it will spiral out, okay, and decay, and the rate of spiraling out will, of course, depend on the temperature. Here's where we can talk maybe about the mutual friction. What is interesting in this method, by construction, it's two equations. So I have two observables. I have the condensate density, which has my vortex, which is moving around. And I also have my thermal cloud component. And what I see is, of course, the thermal cloud will sit around the condensate. It's pushed away by the condensate. But it's also localized. The vortex provides a perfect hole for the thermal cloud to rush into. And so you have the thermal cloud, and as the vortex is moving around, you see there's always a localized thermal cloud at the center of the vortex. This is very distinct to a tracer particle, another particle, or another condensate being in the component. Here's the same system, just a little bit of temperature. And in fact, we have characterized that. I'm not going to show you anything here, but how much additional stuff you have in here is a direct measurement of the temperature of the system. Okay, so it's not just it always has the same amount. The more thermal particles you have for the same configuration of condensate particles, the more particles, the brighter this spot will be in here. So you increase temperature, unsurprisingly, this decays faster and faster, so it spirals out a lot quicker. You can see here sort of a 3D image of that. Now this is, I would like to stress, this is effectively, it looks like a vortex, well, it's infilling of a vortex in the vortex core and a bit around it, okay? That's what's happening in the thermal cloud here. It's not a separate vortex generated or anything like that. Okay, so we can characterize that as a function of temperature. We can see at the rate at which the position grows, okay, and we can determine the coefficients that tells us that, which is temperature dependent. And what we see is that it increases very, very rapidly with temperature. There's been some analytical predictions, both saying that there should be some kind of a linear increase, but what we see is at higher temperature, this quickly shoots off, particularly when you include the collisions. At higher temperatures, collisions become important. And in this context, we can characterize like the mutual friction exponents and so on. And there's been some experiment. It's not exactly the same setting. Here we have one vortex. Here they have a vortex dipole, but they tried fitting their dipole picture to our picture, and they claim, well, it's a similar kind of behavior. Of course, this is a bit ad hoc because it's not the same setting, but at least it's not completely different, which maybe is some indirect evidence that this is a correct profile. So what do all these terms then do? Because you asked me about mutual friction, all these extra terms. So in the theory, the nice thing is you have two components and you can add any interactions you want into the model, okay? So what's the key point? You see here this rate of decay. The bottom is just a frequency shift. This rate of decay is actually very high at high temperatures if you include all the terms, but as you include less and less, it has less of an effect. So the key point I want to make here is the C12 collisions, okay? So C12 being non-zero is the difference of this term from those terms. That's where most of the jump actually happens, and that's when you allow particle transfer between the condensate and the thermal cloud, not just the mean field coupling, but the particle transfer. Of course, once you have this particle transfer, having collisions within the thermal cloud will shoot up further the rate. But without C12, that other term would not matter. And the other thing I want to highlight is that if you have a static thermal cloud, so you don't solve this Boltzmann equation, you get nothing. Okay? So you move your vortex through a static thermal cloud, nothing will happen. No decay. If you want to get decay, what you have to do is you have to solve this equation here with a 0. Solving this will actually give you a decay, and these are these green points here. Okay? So the way we start here is we get a self-consistent distribution of effectively Hartree-Fock initially, and then we just it changes dynamically. But the initial distribution is self-consistently equilibrated Hartree-Fock. So, of course, you can think, well, I'm not going to, it hasn't yet been applied to turbulence, that's the next step, but the idea is what happens if you have a vortex lattice, and of course, if you have a vortex lattice, it will decay rather rapidly, and how rapidly the last vortex disappears depends on whether you have a central vortex here or not, okay, but it will decay rather rapidly for the system. Okay. So let me get to the other model then. I told you there's kind of two main models that are being discussed. So in the other model, we treat in a unified way a lot of modes. So not just the condensate, but all the modes that are affected by the condensate, because their properties, these are quasi-particles, not really free particles. So we can't just treat them with the Boltzmann equation. The high-lying ones are fine, but not the ones very close to the condensate. And so we can think of this as a coupling of two systems. And in the standard wave, you have a system described by a Gross-Pitaevsky equation. And then you have this term, which just couples in and out. So it changes particles from one to the other. But this is a random process, so you have to add the stochastic noise term. And of course, this stochastic noise and this dissipation, they're well related. At equilibrium, there's a fluctuation dissipation theorem relating the two. So this is effectively the motivation. The equation that is actually solved is a little bit simpler. It takes this form, and maybe a little bit more familiar. It's 1 minus I gamma, this, plus the noise. You have done some approximations to get here, so it's not the same equation, but what it does allow you to do is you no longer need to treat the dynamics of the heat bath, which you would otherwise need to know. You can treat it as a static heat bath under the assumption that the main thermal cloud, if you like, dynamics are happening in this regime here that is already included within your field. This is no longer the condensate wave function. This is the field up to a certain mode. And of course, the strength of the noise is correlated to your dissipation and temperature. In a statistical sense, what I do is each time I solve this equation, it's like I'm doing one experimental run. And then in the same way as in the experiment, they repeat many times to get some information. This is what we do as well. We have to repeat this many times and then statistically extract some features. So what does a single run versus an average look like? Here we're starting from noise, so we're growing basically to some equilibrium from noise, and you see sort of random vortices appearing in the early structure. So this has the element of stochasticity, it's a single run, and qualitatively it gives similar features to what would happen in the experiment. If you average over them, you're washing out all these things because they're random, and you will get a nice profile, and then you can get global properties like density profiles, correlation functions, and so on. Okay, so that's the idea of how we use this equation. So just to mention a third model and to put all these models into perspective. So here I've told you I have, this is the usual sort of condensed matter picture or the liquid helium picture. I have a condensate, I have a non-condensate, and they're dynamically coupled. Okay. In this case, what I have is a condensate plus a whole range of modes that are affected by the condensate. Their energies are shifted and so on. And I treat those separately, but then nobody's solving this dynamically. The assumption is that this doesn't move very much, so we can mostly ignore it. Okay, so, but effectively it is the coupling of these two that actually gives us the rate that I had, this minus I gamma. And then there's a third model that is basically completely ignoring also the noise and just saying I can solve everything with a Gross-Pitaevsky equation, but then I'm solving Gross-Pitaevsky for effectively a non-equilibrium multi-mode system. So in there is some effective temperature even though you're solving Gross-Pitaevsky. So when would you use each of these? Okay, that can be a matter of quite some debate. occasionally heated, but this method is really very good for getting, say, excitation frequencies. If you're away from any critical dynamics, this is kind of the perfect system to use. So unless you're too close to TC, or unless quantum fluctuations are huge or low-dimensional geometries, this should be the best mode to study. But if you want to study things like phase transitions, critical fluctuations, low-dimensional systems where these are enhanced, then you need to move to at least this stochastic model or a hybrid of the two that doesn't yet exist. The other model here, well, this will get you the same equilibrium as that if you put random initial conditions. What exactly it means when you're running this dynamically, it might depend on your initial state. The idea is there's ergodicity, so very quickly you lose memory of your initial states, and so you can also use it dynamically. You know, people can discuss about that, and I'm happy to discuss further, but it's constrained to give you the exact same equilibrium. So if you equilibrate and then do random perturbations, you will get exactly the same thing, for example, for this system. Okay, so I'm not going to say anything more about that model. There's already too much in my talk, but let me tell you something about these two models. There was a discussion, I forget where, I forget, maybe it was Mark who mentioned that, about, well, we should start comparing these models together. What do they mean? And of course we should. And that was, in a sense, partly the aim of this book. Every person who was working with that theory in the context of cold atoms has written a chapter there, and the idea was they should say in their own words what they think it's good for and not good for, and that's what we tried doing. And then I compared and compiled a literature at the time of all comparisons that had been done in any context. So here's one comparison that we have done, which is relevant to here. And it's exactly this vortex spiraling out problem, okay? So we have two theories. We have this two fluid or two gas model and the stochastic model. So we initiate a vortex at some point. So in the two fluid model, we have to initiate it off center. Otherwise, it takes a very long time to move anywhere. And we look at the trajectory and we see that it spirals out with a certain rate. Then we have the stochastic model. Now, in the stochastic model, the simulations of the stochastic were done by collaborators in the group of, Ashton Bradley. But the idea is they really wanted to show that the stochastic can actually do this kick from the center. So they wanted to start it at the center. But we know that the path is unique for a certain condition. It doesn't matter where you start it. You will always lie on the same path. We've checked that. So the idea is they have many different runs. Each run looks very noisy, like this red run here. But there's huge fluctuations. This is showing you the strength of fluctuation. But if you do a histogram analysis of what is the most likely trajectory, and you plot it on here, you see they capture the same rate. So to some extent, you could say for this problem, these models are fairly equivalent. Now, this is a very controversial statement. We agreed to this paper disagreeing on exactly what all our findings mean. So I'm happy to talk more. But for this purpose, I think it's fair to say that it's good enough that they're at least comparable in this context. For the stochastic GP, exactly, there's a fitting parameter. What is this gamma? This is a very debated thing. This parameter can be ab initio derived. If you want my viewpoint, it's sort of at most order of magnitude good, and to match to an experiment, you always look at the growth curve in the experiment and match to that. However, there have been some experiments, and there are claims by the same group that basically this is completely ab initio and self-consistent and describes everything. I think it's very good, but I would use an effective gamma rather than the derived gamma if I try to describe an experiment. Otherwise, it's just qualitative. But as I say, there's some disagreement on the exact interpretation of that. So one thing that I wanted to note for these two models is both of them actually, if you play around a little bit, they go down to this equation that everyone's using, this effective dissipative 1 minus I gamma Gross-Pitevsky equation. It's just a special case of both of these models within certain approximations. So it's not an ad hoc model, but it comes from this kind of picture. Okay, any questions so far? Any further questions so far on these kinds of things? Okay, now I want to show you, I want to use this method a little bit to discuss some physics and some sort of random vortices appearing and sort of our analog of turbulence, so to say. And most results I'm showing were done by Gary, some were done by Paolo, who's in the audience here. So the question we want to ask is, what process happens when you start from a non-condensate and you get to a condensate? How does this whole process evolve? Okay, so this is a very old and a very difficult problem to address, particularly in this inhomogeneous setting. And so we've tried doing some kind of review of this, which the main things still hold, but it's a few years old now. And more recently, I've written a chapter for Encyclopedia of Condensed Matter Physics. It's on the archive, which is trying to address all these issues about universal features in this context from across different systems. So let us talk about a phase transition. Well, I have a critical point. This is my TC in the context of temperature, okay? But actually it's not really a point. There's a critical region, the region of critical fluctuations. So when I'm trying to cross from something which is not coherent to something which is coherent, there is a certain delay time as I'm going through the process. And then the system is in a very non-equilibrium state, and it has to go through some process of phase ordering until it gets to the final equilibrium. Okay, so there's all kinds of universalities emerging when I try to do something like that. What I'm going to be focusing on is basically how, when you fall out of equilibrium, when you're crossing through the phase transition, you get kind of a vortex tangle, and also phase ordering, which is the process by which this tangle orders itself to get something which is finally coherent. Now, there's other kinds of universality is a very big word. There's other kinds of things. One thing I just want to briefly flag up, if you create very random initial conditions, very non-equilibrium initial conditions, you will see a bidirectional flow, actually, in your momentum distribution, and this has been discussed in the context of something called a non-thermal fixed point. So there's some universal physics there, and it has been recently seen experimentally in cold atoms. And in driven dissipative, so extern polariton condensates, the stuff that Paolo discussed, you can actually map the phase of the system if you start from the very cold side into the Kadar-Parisi-Zhang equation, and then you can actually study KPZ universality features. But I'm not going to be talking about any of these. So, okay, so condensate formation. Now, I'm going to swap, if I have time in the end, to cosmology. So it's interesting how cosmology and condensed matter basically play along quite nicely. So the whole thing of what I'm talking about now about growth came from a paper that Tom Kibble wrote in the context of the hot Big Bang model, trying to understand if cosmic domains and strings form as the universe is created through a second order phase transition. And he's asking the question whether you can actually, because you have an order parameter which varies from region to region randomly, the question is whether you can have any regions which are trapped, like flux tubes in a superconductor. And so this was taken by Zurek in the condensed matter and proposed whether this can be measured in helium or in other systems. And of course, it has been observed, this is the Kibble-Zurek mechanism, it has been observed in many, many systems, starting with helium, but there's a lot more systems, and now more recently cold atoms. Okay. So let me tell you about the one thing about criticality you need to know. When you approach criticality, things diverge, and that tells you what kind of criticality you have. So if you're looking at the condensate fraction curve, and you look at where you have almost no particles, and you ask, what does my characteristic length do as I'm going from the normal side towards this side? Well, it will diverge with the distance from the critical temperature with some characteristic exponent. Okay? If I ask if I'm doing what happens to the relaxation of the system as I approach the critical point, the relaxation time also diverges. So that means it takes an infinite amount of time if you're going infinitely slowly to equilibrate right at the border of the phase transition. And that carries an extra exponent as well, Z, a dynamical exponent. Okay, so now I want to cross a phase transition. I want to start with something which has no particular direction, is a thermal or chaotic field, and I want to go to something which has basically chosen a condensate. This is a non-zero order parameter, and of course I will choose eventually a phase, so localize it at some point here. So if I look in my direction of the quench, from above TC to below TC, as I start approaching my critical point, the system, the relaxation time diverges. So no matter how fast I'm going through here, at some point, all the system cannot follow the same path, and it has to break into small patches because I'm actually going faster than the system can adjust. And this is what these blue lines are meant to show. This is kind of an intrinsic time scale of the system associated with the distance to criticality for a particular quench. And so basically, as we enter the critical region, we undergo this critical slowing down because the relaxation time is diverging. And so the whole system cannot follow the external drive. So my cooling ramp, the whole system does not react as one. And what I get is loads of domains forming. Okay, there's loads of patches forming. Each of them can be sort of quasi-equilibrium, so to say, but there's no correlation between these domains. Okay, and that's the whole idea. That's the whole idea of symmetry breaking at the phase transition. Okay, now by thinking about my particular quench and the way the things diverge, okay, I can actually say, if I'm far enough from critical region, the whole system is reacting, but then in some point, it's just everything is happening locally, not globally for the system. And I can actually write a condition for the special time t hat where this is actually happening, given on my quench rate. And from this equation, I can get some scaling relations. I don't have time to go into detail on that. I'm happy to explain more later. But what we can get is characteristic scaling of this so-called freeze-out time with the rate of quenching, tau q is how quickly we go from the initial to the final state, the critical exponents, z and nu, and so on. And the length scale at this freeze-out time is this psi hat. That's the characteristic length scale of each of these mini patches. And of course, they're separated by defects. So I also have a scaling law about the number of defects with how quickly I'm quenching the system. So all of these can be derived, at least in the context of a homogeneous system. There's been a whole zoo of experiments in cold atoms. Okay, I don't want to go through all of these. I'm just going to be talking about one experiment done in an elongated 3D condensate at Trento. And I'm going to show you a movie of what happens. I'm going to be showing you density isosurfaces at a sort of high and low density, just to see. We start with something completely fluctuating. Then you see all these vortices emerge. It's basically a vortex tangle. It's not turbulence in the usual way that we have heard about it here, but it is the turbulent state. And at later times, what you get is this whole thing through complicated reconnection and relaxation processes reduces to just a few vortices moving in the system. Now these vortices, the motion of them is fixed by the final condensate. So initially, it is sort of critical dynamics. Later on, it's phase ordering, taking account of the potential in the system. Okay, so what's happening? So I have a thermal gas. I'm trying to cool through the critical point. And at some point, a certain time after I've crossed the equilibrium critical point, I can see this tangle of vortices that appears randomly. Each run will be different, but they'll all have sort of a very similar picture. And then you get growth of density. This green area is sort of mostly phase coherent density, but from one side of the vortex to the other, they have a different phase. Okay, so green just shows a certain density. And you see it's very, very tangled up. Okay, it's what I would call turbulent. I mean, we can discuss about the use of the word turbulence here. So then you actually have this relaxation, and by this time it's just vortices moving in a potential. Okay, it's just oriented vortices moving in a potential, and in the end you will get, if you run to very, very low temperature, eventually all vortices will disappear. So the key point is all this critical physics has to be happening in the region around the critical point. But this is not experimentally accessible. So we can characterize things in numerics here and all along the process, but in the experiment, they're actually measuring things down here. That's the only time when they can see, they can count the vortices. And miraculously, the Kibble-Zurek scaling actually persists. The number of vortices is a lot lower here than there. But the Kibble-Zurek scaling, which tells you how many vortices you have as a function of how fast you quench, actually seems to hold, and that's quite remarkable. So just to explain what is going on, if I were to grow very, very slowly, I would just get a nice, smooth growing patch. And if I go very, very fast, I get many vortices. And then ultimately, I might even be left at the same final absolute time with more vortices than if I cooled slowly. Okay, so crossing fast is not a good recipe to get something equilibrium, basically. Now, there's a lot that could be said about Kibble-Zurek. I know I don't have that much time. So what I want to show you is one evidence of this scaling and universality that I said. We can look at the spectral function and look at the lowest momentum mode as a sort of proxy for condensation. Okay, it's in a trap. It's not exactly the condensate, but it tells us something. And I can look at the correlation length. So I can look at the correlation function and see what the correlation length does. And if you look at that, here's how the zero momentum mode occupation grows. Green is a very slow quench. Red is the fastest quench we probed. And the same here for the coherence length. It grows a lot slower here, but smoother, and a lot faster if you have a rapid quench. And the key idea is everything should be universal. In the initial time, if I scale time to this t hat, distance to this psi hat, wave vectors to psi hat again. Okay? And indeed, if I do this scaling, we have analytically obtained what we should be scaling everything against and so on by linearizing the equation. But if I look at that, you will see that everything scales perfectly in the regime where it has to be. So this is evidence that indeed t hat and psi hat are actually at play in the system. Okay, so the findings are consistent and consistent with experiment. And so here's again two pictures. Sometime after crossing the phase transitions, after the critical dynamics, but it's still fairly tangled, and a very late time. So we can map this very nicely in numerics. In the experiment, they can only measure something at this or later time. And what do they see? They see images like this. Here there's one vortex. You can look at it along the thing or from the side, and then you can count the number of defects after expansion. There's one vortex, there's two vortices, three vortices, and so on. It's random in every run, but they get the whole zoo of things, and then they choose which ones they want to focus on. If we would pick from our theory, for example, something analogous, we can show the density from the two directions, but we also have access to the phase, and this is planar phase here, and you can see the type of defect that emerges and how phase coherent the system is. But the point is, the process for going from here to here should normally be universal, but it's a very messy system, very inhomogeneous. So if you want to study this in a universal way, you should go to a cleaner system. And so we swap to a 2D homogeneous system for that. So what do we know? If you have basically a length scale of the system is much larger than all the macroscopic details, macroscopic length scales, then at some point in the evolution, you will get universal morphology of the evolution of the system. So effectively, you're getting these vortex-anti-vortex pairs dying out, and the idea is that overall, the sort of patterns in this picture look similar to that if you would zoom in on a different scale. So if you would zoom in somewhere here, it would look statistically like something here. And the idea is then you can scale everything, and you can say that the correlation length, so the idea is you measure the normalized field at different positions. It has to scale with a characteristic universal function as a function of a growing length scale. Okay, clearly the distance between these is much larger than here. And so if you look at the correlation length, you see that it is growing here. But if we look into the right regime and we scale, you can map all of these into a single curve, and you can determine this form of this universal curve numerically. You can characterize what is this length scale as a function of time, and you can see that in a certain regime it acquires the universal dynamics it's expected to do. And you can get the same information from the decay in the vortex number. And this, I'm going to go fast through this part because I want to get to the last part and I'm conscious of time. This basically holds whether you have dissipation or not in the system. The only thing that changes a little bit is your universal exponent. But we have done that very clearly. And we have seen if you have a dissipative model, you have to have some logarithmic corrections, and this is standard. For example, there's similar models in 2dxy. This is well-known. You have these logarithmic corrections from the vortices. If you have a conservative system, we've characterized for the first time, resolving a debate going on for many decades about the nature of sort of conservative versus dissipative and open quantum systems. You do get perfect collapse, but the exponent is actually somewhat different. Okay. So that's all I wanted to say about cold atoms. I have about, I'm guessing, sort of 5 to 10 minutes left. something like that. So I want to get to this cosmological thing and talk about sort of turbulence. And let me try and motivate this. So I'm not a cosmologist, by the way, that's clear. So here is the large-scale distribution of the universe, and here's what we expect the corresponding dark matter distribution to be. And the idea is, from seeing this, we can extract information about what we expect the dark matter to be, and then we need to understand what gives rise to the dark matter, which is a significant part of what's going on in the universe. So there is, of course, very, very good models, right? The cold dark matter model that people use, known as CDM or lambda CDM, it's effectively n-body simulations, or if you like, it's a Boltzmann equation. They're solving a Boltzmann equation for particles on an insanely huge scale, right? These are insanely huge time scale. This is the largest calculation done to date. So if you look at things, the large scale distribution far away from any kind of peak, far away from the center of any galaxy, actually is very, very well tabulated and understood. But there's some problems about what happens in the smaller scale, so on the range of galaxies, okay? And so there's an alternative model has been proposed. Let's take it one step basic. So if I have something with a certain momentum, it will have a de Broglie wavelength, okay? So the momentum can actually depend very heavily on the mass of a particle. So if I have a very light particle, okay, this is something like 10 to the minus, I don't know, 50 or something kilograms. It's extremely light, okay, many orders of magnitude colder than atoms or extern polaritons or so on. Basically, the de Broglie wavelength is of the order of a galaxy, okay? So then you can think of a galaxy as being a condensate, and you can have galactic scale condensation, and this is going back quite some time now. So the equations you would solve to model that would be basically a Schrödinger-Poisson equation. So you have the gravitational field here, okay, that obeys the equation. But of course, you might have some interactions, contact interactions between these axion-like particles. Okay, so this is like a Gross-Pitayevsky plus gravity. And it turns out that when you solve this equation, it turns out that rather than having a divergent, rapidly divergent density towards the center, it regularizes it quite a bit. And it's more consistent with what people believe on the basis of what the data are showing. So this model seems to actually work quite nicely, at least for some observables that conventional CDM does not incorporate, does not fully describe. So what do we have if we go to a wave picture? Okay, effectively we have these hydrodynamic equations, and as well known, we have this quantum pressure term, right? So what happens is basically gravity is pulling everything together, and then the quantum pressure is keeping things from collapsing. And so what you get is a so-called solitonic core, which is effectively a galaxy, okay? Each of these solitons is a galaxy. Now, simulations not done by us from cosmological conditions, if you would do CDM, you would get something like that. And from the same initial conditions, if you would solve with this model, you get this. As you can see, there's a very close analogy. It might not be 100%, but it's effectively the same thing from the same initial simulations. So this is actually... This is a condensate equation, effectively Gross-Pitayevsky, and this is Boltzmann equation. Well, actually, this is just a problem that's dating back many decades about the link between kinetic equation, sort of kinetic Boltzmann equation, and classical field or Gross-Pitayevsky description. In some regimes, they give the same stuff. So what we've done is focused on one of these, generated one of these solitons, and tried to analyze its coherence. So on a log scale, okay, pay attention, this is log scale. Here is your inner core, the soliton, and then this is the large scale one. This large scale is very well understood. The problem is only here in the middle. And there's various ways to characterize. I don't have time to go into the details. What we've done is we've looked in detail into the coherence of that system. And what we find is if I describe it as a condensate and I do my same analysis as I do for the stochastic equation to ask where is the condensate, what's going on, I would get this green curve. So the soliton is actually a perfect condensate, and then everything else is something else. So you can see here's my condensate density extracted self-consistently from numerics, and here's the total density. So we have characterized this. The inside is fully coherent. I don't have time to go into that, but this is like a perfect condensate, like nearly 100% coherence. But what is interesting is, so we have this purely coherent high-density core, but what this is actually surrounded by is this picture here. So I have over and under densities, and between them I have vortices emerging. Okay? Now, what does that mean? Let's look at this movie. Here's my core on a normal scale, not log, and effectively this is around. So you see you have all these vortices that are actually moving around. You can see they are vortices. You can look at the phase around them, and the phase does change. And they never enter into the core here. Okay, they always stay around the system. And we got a mention of that on phys.org and a few more dubious websites as well. In terms of thinking about turbulence now, so here we have no interactions, okay, G0. We have no interactions, and what you have here is the solitonic core. And very quickly, because I'm out of time, the quantum pressure is dominating inside, okay, as you would expect. That's what's keeping the system going. The compressible energy is larger than the incompressible right at the core, but then when you go outside, this is reversed because effectively, and the total energy, classical energy and quantum energy are the same. And effectively, if you add repulsive interactions, you will get something slightly different. The profile is different. It doesn't have the core. And the quantum pressure now becomes subdominant when you actually have strong interactions, because interactions are keeping the thing from collapsing. They're repulsive. And interestingly, if you look at the incompressible kinetic energy spectrum, you get a nice peak corresponding to this intervortex distance, and you get a k to the -3 scaling, indicating that these are indeed quantum vortices. So I just want to show you this analogy between cold atoms with a double profile and exactly the same analysis for this fuzzy dark matter. You have a coherent core, and then you have the other stuff, which is the non-condensate. So this is basically two-fluid model all over again, but now for cosmological systems. We have formulated these equations. I don't want to bore you, but we have actually formulated all these two-fluid model in the context of cosmology. And in principle, this set of equations, I can take two limits. One will give me cold dark matter, and the other will give me fuzzy dark matter, and this model just incorporates the interaction between them. So the idea is here, everything is so dense from gravity, it's basically a condensate, and around here you can think of it just as particles. So the idea is to hybridize those two pictures, and then interestingly there's turbulence all around. So I know I've exhausted my time. My clock says 56 minutes, sorry. So just as a summary, basically I hope I've told you sound emission is very interesting in a quadratic trap, and I stress the word quadratic trap, and I think there's still some open questions here mathematically of understanding this interaction in a quadratic trap. I've shown you how some kind of turbulence emerges when you quench a system through the phase transition, and also the turbulent relaxation is somehow related to the decay of a turbulent state, but of course it's not self-sustained turbulence. And then I hope I've told you a little bit about, at least within this model, how you can have an analog of cosmological dark matter turbulence. So thank you very much for your attention.